of a given frequency. So I'm just going to make a little function that can automate all of this for us. So signal power equals just copy this. And then the sine wave is going to be the same thing, but without the shift.
It's not up.
Pardon?
You're still on the OHP.
Oh, sorry, I beg your pardon. Thank you for pulling out. So I'm just writing a little function here, which I'm going to give a given frequency and a given the vector between 0 and 1, which we called time earlier, and the signal we want to test. And I'm going to make a local copy of a cosine wave and a local copy of a sine wave. And then I'm just going to return the hypotenuse of the triangle made by the correlation scores with each one. So that's signal. Plus. This backslash just means you can carry on a new line. So fit it all in. Correlated cosine wave. Signal. Okay, so we've defined that. So now let's just test it. Signal power is equal to 2 times by time times by. So I'm going to call this now to test it. So we're going to say I want frequency. The first argument is the frequency to this function. So 2 hertz, this time thing we defined earlier, and I'm going to give it a sine wave with a random shift in it. So first we set the frequency, then we set the shift. Pi over 3 point whatever, just some random shift, and it should hopefully print a score of 50, because that, or close to 50, because this should give you the correlation score regardless of the phase of the input signal. And I probably need to print signal power into. Oh no, I can't call that. Whoops. This is demo effect coding. There we go. Yeah, so the score that returns is about 50, which is what we expected. So it doesn't matter what shift I put in here. I could offset it by 90 degrees, and we should get about 50. I could offset it by anything, and we should get about 50 in there. So that's basically how you find a sine wave of a given frequency, regardless of the phase. There's another thing you might want to do with an incoming signal. We're assuming we know what the frequency of the incoming signal is at the moment, but you usually don't know that. So I'm going to write a little thing that can you see in principle that if you don't know what this thing for a given frequency tests how much of a sinusoid of that frequency is in it. So if you want to get a sort of graph of how much power there is at different frequencies inside your signal, all you have to do is run this function a bunch of times with different frequencies, so you can get a score of how much there is at 1 hertz, and a score for how much there's at 2 hertz, and a score for how much there's at 3 hertz, just like that. We should be able to knock up that quite quickly. I'll just get rid of this. So I'm going to make a list of frequencies between 0 and 5 hertz with, say, 100 different steps. And then I'm going to just pre-allocate an array to put the answers into. And then I'm going to generate an example signal that we're going to give it. So it's just a signal of with a random shift with a frequency of 2 Hertz, and we're going to test the we're going to see between 0 and 5 Hertz how much of each of those frequencies there is in the signal. So AX. Oh, thank you. That's going to fail, isn't it? Thank you. Signal power. Pardon?
Signal this time.
Yeah. Thank you.
Little debugging experts.
Yeah, exactly. Run the code in your head. I don't have to do any of this. So this is all a bit laboured, for which I apologise. But so what we're seeing here is we're just saying take this list of input frequencies between 0 and 5, 100 different frequencies, evenly spaced between 0 and 5, and call this function signal power to see how much of that frequency is in the example signal, which we just generated up here as an example with a frequency of 2 Hertz. So what we're probably expecting to see when we plot this is on the bottom between 0 and 5 and the frequencies and the power on the vertical axis. And you might expect to see a big peak at 2 because it's at 2 Hertz. It won't be a perfectly big peak at 2 and nothing anywhere else, because that would only work with sort of an infinitely long input signal, and we get funny effects at the ends which corrupt it slightly. But you should see that basically this graph. Oops, I didn't mean to do that at all. What did I do?
Hit the home button at the bottom left of the graph page.
Go up a page.
No, run it, execute.
Yeah?
Yeah. And then on the bottom left of the figure.
Oh, I beg your pardon. No, that is.
Button next to it. No. Okay.
No, it's still at 5 Hertz. It was right when it first printed, so I must have just accidentally hit something.
You've got, when you enumerate, you overwrite the frequency variable. So when you ran it again, that had the last value, which was 5.
Oh, okay.
So now it's 5 when you generate the example.
Okay. That's tedious.
Just rename it so that you can run the
Yeah.
first time again. You still need to set frequency equal to 2. 3 equal to 2.
Oh, I beg your pardon. Okay. Oh, yes. No, I've done something completely stupid here. I'm sorry. Yeah. Right. Sorry about that. Okay, so that should work. Okay, right. Sorry. Thank you, guys. So basically, this is a graph showing that most of the power in the signal is at 2 Hertz. So we can now look at a given signal and find out how much power at different frequencies there is, regardless of the input signal, which is a useful general thing in signal processing. And this thing is often confused with the Fourier transform. It's very close to the Fourier transform. It's actually the power spectral density of the signal that Matt was talking about earlier. So it's basically saying most of the energy of that signal is 2 Hertz. So this is all a bit forced, but hopefully we're sort of all on the same page now. There's one other thing I want to show you before we actually dive into the GPS and it starts to get a bit more exciting, which is we've talked about how sine waves correlate with each other, which is where you have a good correlation score, and then as the phase drops down to 90 degrees, you get 0 correlation score, and then it goes negative, and then it builds up again. There's another useful thing we should look at, again, with reference to Matt's talk about noise. So I can make a vector of example noise, so just like a vector 100 long of complete random gibberish mostly between 0 and 1. Which is that, right? So it's just rubbish. It's just randomly generated stuff between 0 and 1. And then we can see how well noise. In fact, I'm going to make this a bit longer just for the demo. So that's just 1,000 random points all plotted with the average is 0. We can we can look at how noise correlates with itself if you shift it a bit, as opposed to how sine waves correlate with themselves if you shift them a bit. So that's 1,000 long, isn't it? So for shift in. Oops. So that's just going to generate shifts between 0 and 999. Going to be equal to correlate example noise. And roll example noise shift. In fact, so what this is going to do is it's going to say fill up this array which we've fill up this thing of results with the correlation scores of when we correlate example noise with the same bit of noise but just shifted a bit. So it sort of shifts a bit to left and takes the M values and puts them on the other side. So how well does it correlate with itself if we move it relative to itself? And just to make the graph plot with 0 shift in the middle, I'm going to shift everything so it's symmetric about 0. So it's going to look like this. And correlation scores. Okay. Oops, I didn't shut that down from before. Why is there a blue line there?
Still plotting the noise at the start.
Thank you. That's not going to work. Right. So this is a really quite useful graph. So it's basically telling us that if you have a random bit of noise, if we completely perfectly align itself with itself, i.e. with a shift of 0, the correlation score is really high, obviously, because it's identical. But the second you move it relative to itself, even a little bit, the correlation score basically becomes 0 for any other shift. So we've completely rolled it back round on itself, because it's 1,000 long. We've rolled it from 500 to minus 500. So anywhere other than perfectly aligned, nice big score. Sorry, anywhere other than perfectly aligned, 0 score, and otherwise a nice big score. And that's an incredibly useful property for GPS, which we will hopefully now come on to. So I apologise if that was all old for some people, but that's basically all the signals we need to understand how GPS works. So, how does real GPS work? Well, it's kind of tricky for the satellites because they only have transmitters of about 10 watts, I think. And with that 10 watts, they have to more or less cover an entire hemisphere of the Earth. So if you actually do the maths for that, you find that your received signal on the ground is incredibly, incredibly weak. It's a much, much harder problem than receiving from HABs when they get close to the noise. And in fact, with GPS signals, the GPS signals you receive on the ground are about 15 decibels weaker than the thermal noise of your receiver. So that's just the noise in your receiver, even without an antenna on or anything. It's just sitting there humming with its own temperature that generates radio frequencies and stuff. So you might say, well, all is lost because it's like a mouse whispering in the end of a shouting room. You just can't hear it. Except you can if you do some really clever stuff, which is what GPS does. So I've got, I'm going to open, just to show you what the kind of thing you get looks like if you were to just plug in your RCL, your SDR dongle, set it to the right GPS frequency and listen for a bit, so I can show you the signal you'll get. I can tell you in advance, because it's beneath the thermal noise floor, the actual signal, you are just basically sampling the thermal noise floor. It just looks like noise, but I'll show you anyway because we need it for later on. So I've taken the liberty of getting some already, which I called example data.bin. And I just want to read from it. I'm going to put it into... so a little note about the way this data is packed. It's actually the ADC that was used to get this data is only 1 bit, so only either outputs a 0 or a 1. And the way it's saved that in the file is that it saved that output per bit. So there's 8 samples per byte, because a byte is 8 bits. So it's just 0, 1, 0, 1, 0, or whatever it happens to be. So we're going to have to unpack it into a nice array of numbers that we can use with our maths. So I'll just do that now. So I'm just telling what kind of data that we're expecting to Python. No, I don't need to do that. And then, so that's going to split it up into a list of individual bits from this lump of bytes called raw data. And these are between... I just need to tell it that it's this is all just kind of housekeeping stuff, just to convert it into a list of numbers we can use. But so because these samples are either 0 or 1, actually it's really useful in signals to have everything between 1 and -1, because that means when you multiply them all together, they still stay within 1 and -1. Whereas if you had it, say, between two signals between 0 and 2 and 0 and 2, and you were to multiply them together with a correlation or whatever, you get some which were 4. If 2 2s are aligned, and eventually everything can run off the precision of your numbers. So you just keep everything between 1 and -1, and it will always stay there. So in order to convert from 0 to 1 to 1 and -1, it's really simple. You just multiply it by 2 to get it between 0 and 2, and then subtract 1, so it's between -1 and 1. And then that's quite a big file, so I only want 1 second of it to play with for this. Equals bit data. So the sample rate was 12 megahertz for this. So 1 second is 12 million samples, 1, 2, 3, 4, 5, 6. And then I'm also going to get a millisecond of data for a reason you'll see later. I want to spell that right. Second of data equals, which is just a thousandth of that, so 0 and 12. So this just means give me all the samples between 0 up to 12 million, and this gives me all of it up to 12,000. So that's just the first 12,000 samples. So the way the receivers work that we use to sample this is it's first taken the GPS signal, which, as I'll come on to in a second, is up in the gigahertz range, 1.5-ish gigahertz, mixed it down to so that the GPS signal is at 3 and a bit megahertz. So I'm just going to tell NumPy for later on that the center frequency of the GPS is 356 3000. And that should hopefully just work. With luck, yeah. So okay, so slides. So we've got this problem with. Oh, actually, I was going to show you what the data looked like once. I beg your pardon. I'll just plot it quickly. Plot millisecond of data. Yeah, that's stupid, isn't it? I'll just plot the first 100 samples of it. So you can see they just be randomly distributed between -1 and 1. Yeah, so just randomly either 1 or -1. It's basically the same as before with the random noise, but just clipped to 1 or -1. So Yeah, so the GPS has this problem that its transmission power is not nearly enough to sort of conventionally just send like RTTY or whatever, because we just wouldn't hear it on the Earth. So it has to do quite a clever trick. So again, GPS is only ever telling you that basically what the paper airplane said, which is I am here, and this is the time. And all the receiver on the ground is trying to do is what we did earlier with that bit of geometry, which is compare the arrival times of each one. But the receiver has to be able to hear the GPS signals. So what they do is, we saw earlier, there's this really clever property of noise, that if you get a random bit of noise and perfectly align it with itself, it scores really well. It has a really high correlation score. If it's slightly offset either way, then the correlation score is rubbish. So what if they said when they were doing GPS, what if you could encode the GPS stream with almost like a kind of specific kind of random noise? And if the people on the ground knew precisely that kind of random noise it was modulated with, then they could hunt around in this crap that they were getting from their analog to digital converter. And if they happened to find precisely the right sequence of random noughts and ones, they would get this big correlation score, just like what happened with the noise earlier. And so that's what they do, and they use something called spread spectrum. So they have data that they want to send. It's actually 50 baud, just like our normal RTTY, the actual data they want to send. But they use a technique called spread spectrum, where they basically spread that out by, instead of just sending naught and then 1 and then naught when they want to send some data, like this, say. So let's just say this is a random bit of data at 50 baud, so 20 milliseconds, 40 milliseconds. Oh, sorry, people. I think I can zoom out, actually. Okay. Can you see that? Yeah. What they actually do is they have a second signal that they mix this with, and that second signal runs much faster. It runs at about megahertz, it's 1.023 megahertz, and that second signal is a sort of basically random sequence of ones and zeros, but a very specific random sequence of ones and zeros that's unique to each satellite. And so what they do is they add this signal, and it's 1,023 bits long, and it's sent at 1.023 megahertz. So therefore, each of these 1,023 bits takes 1 millisecond to send. And what they do is they send that specific sequence, unique to each satellite, called its PRN, or pseudo-random number. They send that 20 times per bit. And then, so let's pretend, this is just a silly cartoon that I've drawn. They're actually called CA codes, which means course acquisition codes. So pretend this is much faster than this. So these are the things that are sending 1,023 bits every millisecond. And this is the data they actually want to send. And what they do is they exclusively OR, or XOR, the data signal with this pseudo-random bit stream. So exclusive ORing is just basically, it's basically the same as binary addition. So 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 0 equals 1, and 1 plus 1 comes back to 0. So if there's a 0 and a 1, the sum is 1. Otherwise, the sum is 0. So so this is the modulated data. So it's just doing what I said. So basically, where there's a transition and these are both 1, say, the answer becomes 0. And then when it's 0 and 1, the output becomes 1 again. So it's just binary addition. And then what they do is they do binary phase shift keying to actually send the radio data down to Earth. So this bit stream here is only at 1.023 megahertz, and they have to modulate it up to the GPS frequency. The GPS frequency is 1.575.42 gigahertz. So yeah, 1575.42 megahertz. And they have this carrier on board, which is just 175.14 megahertz. And all they do is, all binary phase shift keying is they swap the phase by 180 degrees every time there's a bit shift. So for example, this is just the raw carrier, when it sees, say, the change of sign here, it would just swap the phase 180 degrees. And that's all phase shift, binary phase shifting is. So that's an example. That's an example output. Now this is a slightly silly cartoon because of course there's like thousands and thousands of wavelengths at this high frequency per bit. So it looks a bit munched up here, but you get the idea that you get these phase shifts. It suddenly rapidly changes 180 degrees. As if mirror imaged every time there's a bit change here. So that's what the GPS satellites send. And our job on the ground is to basically try and hunt around in the sea of stuff that we're receiving on the ground, looking for a GPS satellite signal. And the GPS satellite signal will be modulated with one of these specific codes, again, one per satellite that we know in advance on the ground. So we hunt around in the signal we're receiving, looking for something that looks like it's this unique sort of signature of the GPS satellite. I'll come on to that in a second. So the satellite is sending, every millisecond it's sending this pseudo-random number, which happens to be 1,023 bits long. 1,023. And we on Earth are just sampling stuff, looking for it. We're trying to find a satellite in amongst all of this noise we're receiving. So the way we do it is, the way you receive GPS signals is to first hunt for all the satellites that you can see in the sky above you. And then once you've got them, you have to sort of track them and listen to them so you can actually get their original navigation data out. Navigation data out here. So if you can imagine you're on Earth and you just grab a millisecond of data from your receiver, you don't know if your millisecond is particularly aligned with when the satellite was transmitting its millisecond. So if you just grab a random millisecond of data, you might have accidentally grabbed that bit, which is going to be the end half of one pseudo-random bit sequence and the first half of the next one. So the job of the receiver first is to hunt around, grab a sample of, say, a millisecond, and then hunt around looking in it for all of the satellites that it thinks might be in orbit. Oops, oh, that's on. That it thinks might be in orbit. So the way it does this is a bit like this. And this is just stuff we were talking about earlier. So let's say it grabs a millisecond of data coming in here. What we're going to these circles with crosses in them, time symbols, just means multiply. It's the same thing as mixing. So coming in here is going to be this kind of modulated signal that we talked about earlier, except hidden under the noise. Then we have to hunt around for the pseudo-random numbers. We have to multiply the incoming signal with an example pseudo-random number. So say there are 32 satellites and each one has a unique one. And say we pick satellite 23 as an example. We multiply this hunk of signal by a pseudo-random number, a guess at the pseudo-random number. And then we do this, then we basically, what comes out after that, hopefully, is that will be just the sine wave left. So we're basically just doing exactly the opposite of what took us from this to this, which was multiplying by that. We're doing that in reverse. So we hopefully should just be left with a bit of sine wave. We discussed earlier how you hunt for a random bit of sine wave in a bit of sample data. You multiply by your local sine wave, which we can call I for in phase, and you multiply by the local cos wave, which is the 90-degree shifted version of the sine wave, which we call Q, or for quadrature phase. That's pretty standard terminology in radio stuff. So this is basically just the sine and the cosine wave, and then we sum them, having multiplied them, we sum them together, and then you square them, and you get basically the correlation score output. I was square rooting it before, but you don't have to. And then because I talked about this issue of you don't actually know precisely if you've got your pseudo-random number generator precisely aligned with the incoming signal, you actually have to try this for each and every possible shift combination of the pseudo-random number. So, for example, shifted by 1, shifted by 2, all the way up to 512 or whatever it is in each direction, which is quite tedious. And then the added problem is that, of course, the UKHAS satellites are all moving in orbit relative to you, so they've got big Doppler shifts relative to you. So you have to both look for the signal with all the pseudo-random shifted, with all the different possible shifts of the pseudo-random number in this millisecond of data you grabbed. And you also have to look at a whole bunch of different possible carrier frequencies because of the Doppler of the satellites relative to you. So it's a really big search problem. So how are we doing for time? Good. So I'm going to have to write a bit of code now. In fact, what we could do now is I'm going to have to write a tiny bit of code. So if we want to take a 5-minute break now, because we've been doing this about an hour, that could work quite well. And then when we get back, we should be able to look at trying to acquire the GPS satellites and the noise.